Morning, everybody. Today we have the pleasure of having Charles Mahan, who is an associate professor of the Department of Chemistry at the University of Virginia. Professor Mahan was born in Madison and raised in Wauwatosa in Wisconsin, USA. In 2012, he obtained his PhD in organic chemistry at the University of Northwestern in Chicago, under the supervision of Chad Mirkin. And during this period, he received the Edmund Wellewis Award for senior graduate students. After that, he was working in the group of Clifford Kubiak at the University of California, San Diego, as a postdoctoral research. Finally, he joined the Department of Chemistry at the University of Virginia in 2016 as an assistant professor, and since 2022 he has been associate professor in the same department. In 2024 he received the Bessel Research Award for the Alexander von Humboldt Foundation, and his research interests are centered on catalysis using abundant small molecules like carbon dioxide, hydrogen, or oxygen at the interface of molecular electrochemistry and materials. Today, Professor Mahan is going to present a talk titled Metal-Free Molecules as Electrocatalysts and Co-electrocatalysts. So it's a great pleasure to have you here, Charles, so the floor is yours.
Wonderful. Thank you, Luis May, for a kind introduction. And I do realize the error. I know that this is the organometallic invited speaking tour by the Royal Spanish Chemical Society, and that my title unfortunately emphasizes all the things that don't have to do with metals. But I assure you that the majority of this talk is on metals and organometallic chemistry, just emphasizing a little bit of how we supplement intrinsic inorganic or organometallic reactivity with other types of molecules. So as was mentioned, one of the key areas of our focus is on things related to the conversion of abundant small molecules using electricity, right? So if you have renewable electricity, it would be nice to use that as a way to drive and store electrochemical energy. Because in the last 40 years, about 80 parts per million has been an increase in the global atmospheric concentration of carbon dioxide. And in fact, if you go back to about the start of the Industrial Revolution in 1750, and then all the way back 800,000 years, basically throughout the entire existence of modern humans, the levels in the atmosphere have never been this high. So this is necessarily changing things about how energy is captured through solar radiation and other regions of the electromagnetic spectrum. And the reason this should motivate an interest in a lot of things, like carbon neutral and carbon negative, is that what we're trying to avoid is significant changes to what we're seeing in the climate, right? And so the kind of bad news, which should accelerate what we're looking at here, is that if you look at projections done by the International Panel on Climate Change, right? So from this point forward, if we do things like go carbon negative or stay on the same course, what's going to happen in terms of average global surface temperature rise is essentially the same. So it's not really the carbon seen here in color that we're emitting from this point on. It's the bulk of the carbon that we've aerosolized into the atmosphere through several hundred years of industrial usage of petrochemicals. So clearly we need to figure out a variety of solutions to begin addressing this problem, right? And so what is the challenge to using electricity as a driving force to run thermal chemistry, and how are we going to interface that with this idea of we have abundant molecules which would make the most essential substrate, right? So the challenge really begins with molecules like carbon dioxide at their fundamental level. If you look at carbon dioxide in comparison to the simple small molecule allene, it becomes evident if you consider their molecular orbital structures. So I like to use allene here in B on the right because it's a great example for teaching point groups in inorganic chemistry. And that's because those CH2 groups are actually rotated orthogonal to one another. And that's telling us something very important about the pi bonds connecting those two outer carbon atoms, specifically that they are not interacting with one another at all. And as a result, allene is a very competent electrophile in a way that carbon dioxide isn't. In carbon dioxide, the bonding is a little bit different because you see cooperativity across those pi orbitals from oxygen to oxygen. And this high degree of symmetry makes the bonding challenging to begin bending and breaking, because that's kind of the essential component to removing those pi bonds. And if you look at this, there's a secondary problem to disrupting this highly symmetric bonding environment, and that is you're asking lone pairs situated on these electronegative oxygen atoms to come into closer and closer contact with one another. And so this geometric rearrangement has consequences on the electronic structure that can only really be addressed if you think very specifically of properties at the active site. Because what you're doing is trying to drop an orbital low enough in energy to begin functionalizing and breaking these bonds, right? Ideally using the relatively electropositive carbon here in between the oxygens as your point of initial functionalization. And so the way we think about this is, of course, beginning from inorganic chemistry, unlike my title would otherwise suggest. And that's because inorganic coordination compounds give us this fantastic illusion of control. We have something we can make, crystallize, characterize, and we can think about understanding reactivity as it relates to structure if we begin systematically modifying it and understanding it mechanistically. So the basics, of course, would be ligand coordination motif for the types of heteroatoms we use, but we can also begin thinking of the broader reaction environment near the active site and how groups not necessarily attached directly to the transition metal center might impact the way the reaction occurs. And of course, this isn't an idea original to us. We're borrowing this from nature, where enzymes have evolved over the course of millions of years to use these types of interactions to run essentially electrochemical transformations near the thermodynamic potential reversibly at very high rates. And so if you look at it from the inorganic chemistry perspective, of course, the first thing you might focus on and notice is this supporting iron-sulfur cluster, this nickel-iron active site in CO dehydrogenase, which can interconvert CO2 and CO very rapidly. But that's not the only reason that this works well. If you think about the potential energy surface for a transformation, I want to run reversibly. If I'm going to optimize that catalytic process, I want to avoid barriers that are overly high, and I also want to avoid wells where something is so stabilized it slows the rate I'm able to achieve from reactants to products, or in reverse. And so one of the unfortunate things about modifying only at the metal center is you tend to change that potential energy surface in a unified way. Let's say I make it more electron donating because that lowers a barrier. More electron donating properties at a metal center could also overly stabilize something in the catalytic cycle and then slow the reaction down for completely different reasons than those were being initially addressed. And so the trick from nature here is that we've got, of course, histidine and lysine as pendant residues. They're interacting with substrate bound to the active site. So they're not directly electronically connected to the metal centers, but they're affecting the way barriers and wells appear on the potential energy surface. And so there's a potentially very powerful way to think about that broader environment as a way to tune this. And so I apologize for those of you to whom this is very familiar, but I think it's a good starting point for understanding how we extract mechanistic information from these systems, where we're trying to use electricity as a driving force for electrochemical processes. So for a homogeneous compound in solution that's dissolved in solution, you can have a reversible electron transfer. And so when you look at this by CV, you get this wave where the forward sweep is very symmetric to the reverse sweep. Now right here at the midpoint between these two waves is the standard reduction potential for the system. That's because in an electrochemical cell, if you look at it through a Nernst equilibrium perspective, at every potential, I have some ratio between the oxidized and reduced species. Now, voltage is, of course, a thermodynamic readout of the system. If I introduce something that perturbs this equilibrium, right, of P and Q, I'll see shifts in that reduction potential proportional to the thermodynamic change that has happened. So voltage is giving me a lot of information about the thermodynamics of what's going on for electrochemical reactions. Now let's imagine we're establishing this equilibrium and Q is a very reactive species. Now we have a catalytic process where, according to some rate, we're consuming that activated species as it's formed. Now, if current is a proxy for the kinetic information, and we're not seeing a change in the catalytic rate mechanism, we can relate changes in concentration to how they change the apparent turnover frequency of the process. And in doing so, you can start to tell how substrate dependence or catalyst dependence is affecting that catalytic process as a component of understanding the mechanism. So the name of the game then would be to decrease voltage and increase turnover frequency to the best that we're capable, because that would represent a high degree of energy efficiency and a very rapid catalyst. So one of the first things we started looking at is this chromium compound. It's a formerly 3+ oxidation state, and we're kind of inspired here by Jacobson's catalyst. But the thing about metallosalins, like Jacobson's catalyst, is that generally we're forming those ligand constructs through condensation reactions, right? We're taking an imine, an amine, and an aldehyde to make an imine bond. That means we're necessarily in an equilibrium with water, which can be a problem when water is something that's going to be present either in the reaction medium or as a substrate or product of the reaction process we're actually looking at. And so quite simply, the idea was to protect that potentially reactive imine bond, where radical character can localize and also create problems, in this aromatic bipyridine framework. And so we're creating a spot where an electron can pass through the electrochemical process. We're going to modify the way the molecular orbital looks in the reduced state because of this redox activity, and then begin to study the electrocatalytic properties. And so when we look at the CV data, with carbon dioxide and phenol present as a weak acid, what we see is that only when those two are combined do we see a switch to this irreversible catalytic process. And so if you poise the electrode here past this reduction potential and pass enough current over time, you can relate the number of electrons which have flowed through the system to the amount of product you're seeing by characterization. And in this case, we see an almost absolute selectivity for carbon monoxide, which is a 2-electron, 2-proton reduction product from CO2. Now what's nice here is that the overpotential for this system is relatively low. Every 59 millivolts equates to about 1.4 kilocalories per mole, meaning that we're very close to kind of low energy input to drive this reaction. The problematic aspect, of course, is that we're not really operating at a very high turnover frequency. But we'd like to improve this turnover frequency while also not sacrificing necessarily the amount of overpotential we have to apply to the system. But if we use those mechanistic approaches like I talked about, varying concentration, we can establish a catalytic rate expression for this process, which is first order in catalyst, carbon dioxide, and that weak acid phenol, so in DMF solution here. Now this is not necessarily an unexpected result for most molecular catalysts, but what is different here is what the putative active state for this process might be. If we're starting formally from chromium-3, the activated species has 2 electrons in it. We would say formally that would be something along the lines of a D5. And the reason that's not necessarily expected is because over decades of research on molecular electrocatalysts, the design paradigm which has generally emerged is that what you really want is a later transition metal. You want a very reduced, low-valent late transition metal with a DZ² orbital that's potent enough to act as an electrophile to do all that work of bending and activating CO2. And so we see a variety of these catalysts. Iron porphyrins, first reported in 1988. Cobalt and nickel cyclam type species, first reported in 1980. The Lane catalyst in 1984. The success of these compounds and their good reactivity led to kind of the assumption that, well, the nature of this reaction is that we're biased towards needing a late transition metal. Earlier transition metals than group 7 here, it took until 2011 to discover that manganese worked as well. But these earlier metals, right, they're essentially non-existent. And so first in 2014, there was a report on molybdenum and tungsten. But if I'm looking at these are 0-valent 18-electron compounds. It's going to be hard to reduce them. And if I'm reducing them, it's going to be hard to convince them to release CO to create a vacant site. So these are kinetically limited, and thermodynamically, there's a pretty significant penalty. The only reactivity which had been known with the chromium analog was dependent on the electrode material you used. You needed a gold electrode because it helped labelize CO from this chromium-0 compound in order that you could actually react with CO2. And so at the time, I was very fortunate to have a very talented postdoc who's in the audience today, Wanho. And Wanho helped us look at this a little bit computationally, and it turns out why this system is so selective is in part related directly to this idea that the bipyridine ligand is participating. So rather than a chromium-1 species, what we really think this species looks like, or the best description we have to this point, is that of a chromium-2 species with a BiPi radical anion antiferromagnetically paired with 4 unpaired spins on that chromium center. And so the molecular orbital is distributing things, which it turns out is good because CO2 is easiest to activate if you think of it as more of a pi acid, right? Because you want to break carbon-oxygen bonds. And so in this case, if you compare that then to what should be thermodynamically preferred, the protonation of the chromium species to make a hydride, what you see is that there's actually a large amount of spin restructuring that needs to occur because, again, you're looking to activate this hard electrophile proton here. So you need a restructuring that's actually prohibitive kinetically. So the barrier to forming that thermodynamically preferred hydride en route to dihydrogen generation actually doesn't occur appreciably because we've got this equilibrium CO2 binding step, which is slightly uphill. And when we have those very weak proton donor sources present, we can rapidly consume this end of the equilibrium and drive the catalytic process. So through a series of mechanistic and computational studies, we've established a proposed mechanism for this process. Beginning from the neutral 4-coordinate species, you have a 1-electron reduction to make a 4-coordinate monoanion. Here is our equilibrium CO2 binding process, which is slightly disfavored, but becomes accelerated by the fact that there's a subsequent irreversible chemical reaction, proton transferred to create a hydroxycarbonyl species. Now, this is only basic enough to induce COH bond cleavage if you reduce it again a second time. And it's the 6-coordinate monoanion species, that's the state right before our rate-limiting step of the reaction, where we see water generated as a coproduct and then a CO species, right, a chromium carbonyl. Now, a place a lot of molecular catalysts get hung up is the release of CO, and the reason we think this system is so good at CO release is because we're never actually going to what you might call a formally chromium 0 state. Instead, it's no lower than chromium 2, which means that even if you run electrochemical experiments under a CO atmosphere, you never actually see any interaction between chromium and CO electrochemically in this potential range. And so the two key features which are going to help us optimize this going forward are, of course, the participation of that bipyridine radical anion, both here in that CO2 binding step, but again here in the resting state, where we're actually parking an electron, we think, on the bipyridine ligand that's induced to transfer into the antibonding orbitals for the COH interaction by protonation, right? So a proton-coupled electron transfer step here for that rate-determining step of the reaction. So as I said, often it's difficult just through intrinsic electronic manipulation to make those catalysts more active without paying a thermodynamic penalty to the reaction. And so the idea we've had more recently is again borrowed from how nature directs electrons to active sites. So if you think about metallic cofactors in biology, we have very nice transition metal centers, but they're buried in these largely insulating protein structures. And what needs to happen is electron-rich molecules need to be oxidized, and those reducing equivalents need to make their way to an active site. So in the electron transport chain, of course, we've got an iron porphyrin variant, which is doing the oxygen reduction reaction. That's coupled electrochemically to the oxidation of things like NADH and FADH2, right? So these are redox mediators. Now, what biology is doing is kind of different than what we might need. Biology is creating an energy gradient because it wants forward electron transfer going from those electron-rich molecules to the site where they're being consumed. It makes that a very downhill process because what it wants to do is make sure electron flow goes to the active site. But at its heart, nature is solving a problem that's not unlike the one we have in homogeneous electrocatalysis. Homogeneous electrocatalysis is truly a heterogeneous process because those molecules need to diffuse to the electrode surface in order for the reaction to be initiated. And so, like nature, we have an electron inventory problem. We need electrons and substrate and molecule to meet together in that reaction diffusion layer and actually run a catalytic reaction. Now, where is the advantage of thinking about this for synthetic systems? Well, let's consider a 2-electron process like this conversion of CO2 to CO. If we're activating a transition metal complex to run this reaction, we're reducing it by 2 electrons. The thing about that second electron is, more often than not, because we've reduced the overall charge and we're occupying orbitals, that requires more energy electrochemically speaking. And so we're paying a thermodynamic penalty to activate the compound enough for the reaction to actually happen. Where a redox mediator could play a role here is in distributing that inventory of electrons we need for the electrochemical reaction. So instead of reducing the metal compound twice, I could reduce it only by a single electron. Then my redox mediator could supply the balance of electrons I need for the process, and presumably at much lower applied potentials, I'd be able to run the same process or potentially intercept intermediates for other productive chemistry. And so a really nice example I like to highlight from Victor Mugel and Marc Fontekov is one in where they took this classic manganese bipyridine tricarbonyl electrocatalyst, which is active in only the form where you've reduced this 5-coordinate species again to make a monoanion, and intercepted it by electrogenerating a hydrogen atom donor, which could form the intermediate manganese hydride at much milder potentials. And in doing so, when that species gets reduced, it's capable of being a hydride donor to CO2, and you see an inversion of product selectivity because you're doing this redox chemistry matching at more positive potentials than the intrinsic reactivity. And so now we're making formate a different 2-electron reduction product rather than carbon monoxide. Okay, so we're going to design a redox-mediated system for this catalyst. We want something that's activated near the catalytic response, needs to be chemically stable in the reduced form, and it should be something that's relatively easy to isolate. And so what we'll target here, right, is this idea that this 6-coordinate solvento species, right before the rate determining step, this is kind of our benchmark for trying to figure this out. And so after trying lots of different molecules, what we discovered is that looking in the OLED literature for molecules that are used as part of hole layers in OLED devices is a good place to go, because they're supposed to be stable in the reduced form. And unexpectedly, at least initially, it was this aromatic sulfone molecule that turned out to do the best job of functioning as a redox mediator. So when you added this to solution, what you saw was in the redox response in red here, that this molecule interacts neither with CO2 nor with the weak acid. So no behavior there at all. But when it's present with that chromium catalyst, all of a sudden, there was an emergent catalytic response that originated at the potential at which that mediator was reduced. So this is emergent catalytic properties. This is not intrinsic to either component individually. So the question is, how is this working? Is it an outer sphere or an inner sphere process? So we were skeptical. Wanho was skeptical, at least initially, because it's well known from coordination chemistry literature that sulfones tend to be poor ligands. I'm aware only of this crystal structure from Cotton and Feldhaus from 1981, where there was actually this alkyl sulfone binding to this dirodium complex. So you don't normally assume that that's a strong ligand, so potentially it's entirely an outer sphere process. But as we looked at this more mechanistically and computationally, what began to emerge was a picture where there might be a suite of interactions which are working together to cause an assembly of these two species. So obviously, a dative covalent interaction can be weak, but this isn't the only reason that these species assemble in solution. What it began to emerge was this picture where the reduced aromatic component of these redox mediator sulfones was creating these long bonding interactions between that redox active bipyridine component. So this is atoms and molecule analysis, looking at bond critical points between those two aromatic components. So the assembly of aromatic anions, either with an unreduced species or two diradicals, is known largely from organic anion literature or in polymer literature. But this, if this is to be the case, understanding how synthetic changes manipulate the possibility for these interactions is really going to help us differentiate whether or not this is truly an inner sphere process versus an outer sphere process using kind of mechanistic hypotheses that we can interrogate, right? And so through space electronic conjugation, widely studied for a while, often people make these nice model molecules like 2,2-paracyclophane. where you can create this vector of charge conduction through the aromatic systems by having this kind of rigid structural arrangement where you're positioning them with good atomic registry from top to bottom. Okay, so the picture that began building was at least that pancake bonding could be playing a role for this system when a proton donor is present, because you saw the redox activity of that redox mediator be well matched with that of the bipyridine ligand in that rate determining step prior to COH bond cleavage. Okay? So if this is the case, there should be some evidence of this by manipulating the properties of the redox mediator and the compound itself. So the first idea was, of course, to change the mediator, make a series of different aromatic sulfone molecules. And so what we're changing here, at least for these first two, is a difference of sterics. And then we're looking at the effect of changing redox potential by about 0.13 volts, okay? So if this is an outer sphere process, which you'd expect if it kind of had Marcus-type behavior, is that the more there was a difference between the potential of the redox mediator and the catalyst, the faster the catalytic process should be. Now, in this case, what we actually saw was opposite to that, an inverse scaling relationship between potential and catalytic activity. What was happening as these potentials got closer, the difference in these potentials started approaching zero, was that we saw an increase in activity without losing any of our selectivity for CO. And so what's really happening here is a pre-equilibration of two catalytic species, not unlike Curtin-Hammett conditions. So the first catalytic cycle I introduced was the intrinsic one. That was making this hydroxycarbonyl species. Our rate limiting step is making that water co-product, and then we get that CO, release of which allows us to re-enter the catalytic cycle. Now, what we think instead is happening here is that there's this equilibrium step between the slower form of the catalyst and this faster form of the catalyst, where the redox mediator is actually interacting with the chromium center. So we're displacing that solvent ligand in favor of this redox mediator. Now, what's interesting here is that the reason this changes the rate seems to be purely based on the equilibrium. Because if you look at this theoretically, what happens is that the binding energies get greater as those potentials get closer in energy, but it's relatively invariant in terms of the barrier for that rate determining step. So kind of the way we're thinking about this at this point is, well, what these reduction potentials really are kind of a first order approximation of the orbital energies involved. So bonding, any type of bonding interaction, is of course based on symmetry matching, but it's also going to be it's going to be proportional to the difference in energy between those two orbitals. So if they're closer together, we should get better overlap and we should have a stronger interaction. So lowering that, how negative that potential is actually allowing us to get a more favorable binding interaction because the overlap is better. Okay, so if this is true across this modification for the redox mediator, if we modify the backbone of the complex and increase its aromatic character, that should result in a favorable increase in co-catalytic properties. And indeed, if you swap out bipyridine for phenanthroline, and these two species have essentially the same reduction potential for activation, you see almost twice the turnover frequency for the phenanthroline derivative that you do with the bipyridine, because the redox activity of this phenanthroline backbone is being protected to a greater degree when it gets that radical anion character. And most of these are derived through controlled potential electrolysis experiment, but the relative enhancement is such that it even begins to be apparent in CV kinetics, as just looking at the current. Okay, so if the interaction between these two species is in part through space electronic conjugation and then the dative covalent interaction and probably some dispersion interactions, increasing the properties of the redox mediator's ligand should have a beneficial effect, right? And so what we looked at then was making a phosphol derivative, because this PO moiety should be a much stronger ligand than the sulfone. Crystal structures are ubiquitous with this type of coordination motif. And so at least initially it looked like a good, fair way to increase this, although the reduction potential of this phosphol mediator was a little bit more negative. We did see that favorability in the equilibrium binding interaction. And here, as it turns out, there seems to be a slight improvement in the barrier for that rate determining step. So this should equate to higher turnover frequencies. Now, unfortunately, when you actually measure this, what you see is that while you do improve the intrinsic activity, it's actually less than that of the sulfone. And so if you look at this compound and rotate about that chromium-oxygen bond, what becomes apparent is that this phosphine, because it's a better ligand, has a series of kinetically accessible configurations with a bond between chromium and oxygen that don't have that ideal overlap. These are all within a kilocalorie per mole across a wide range of the possible dihedral angles. So essentially, you're getting kinetically trapped before you hit the thermodynamically stable state. You don't see this with DBTD because the sulfone binding is weaker. It's really funneled to that ideal configuration because that ideal configuration has a well-balanced contribution of interactions between the through-space electronic conjugation and the axial coordination. Okay. So at least going forward, that means when we think about modifying these, we really have to think about this component of achieving the ideal vertical-vertical overlap, because that's where we're actually going to see the enhancement, unlike when it starts getting rotated because of alternative configurations being equally possible in terms of energy. So kind of as a final piece of this component of the talk, what we were very curious about, of course, was the idea that, well, if we have this equilibrium interaction, what happens if the redox mediator is reduced exactly at the potential of the catalyst, but also at potentials more positive than that of the catalyst? So in a normal Toffel scaling relationship for molecular compounds in a reductive process, if the mechanism stays the same, what should happen as you go to more negative potentials to activate the catalyst is you should see an increased rate. You're at a greater overpotential. You should be introducing properties to the metal center where you see a more significant rate. And so if you look at this series of phenanthroline and bipyridine derivatives, you see that they are very nicely ordered across a very normal Toffel scaling relationship, where the harder it is to activate that chromium, the more active the species is in terms of turnover frequency. Now, when you introduce a redox mediator that has the exact same potential as phenanthroline, is more negative than this phenylphenanthroline and more positive than this tert-butyl bipyridine, what you see is that you still get that same relative ordering on the CV time scale, but all of these electrocatalytic responses proceed exactly through that of this BNTD derivative. That's exactly where its redox potential is. And so as we were kind of building to in terms of prediction, we see enhancements when the redox mediator is more negative. That's, of course, the original observation. We see significant increases when the potential is matched. We see slightly lesser increases when that is more positive, but in all cases, it's still functioning as a redox mediator. And as we had tried to predict in tests, we're getting a maximization of turnover frequency when we have an identical redox potential for the redox mediator and for the co-catalyst. But the thing we're trying to leverage here, and what I think is really interesting about this result, is the fact that we can get a co-catalytic enhancement at more positive potentials when the redox mediator is reduced positive of the catalyst, right? So there's no free lunch here. We're making up the energetic difference because of the favorable thermodynamics of the interaction between the redox mediator and the catalyst. And so if the catalyst is active enough, we have reason to believe that we can continue pulling this forward to more positive potentials. And remember, this is working because at that formal standard potential, I'm only 50% reduced, 50% oxidized. In my Nernstian equilibrium of that electrochemical cell, there are small amounts of that reduced species generated at more positive potentials than that value. And that equilibrium reaction is depleting that half of the equilibrium. The equilibrium binding interaction is depleting that reduced half of the Nernstian equilibrium. And what you see is this functional pull towards more positive potentials because you've got this irreversible catalytic process occurring with enough of a rate to drive the reaction. And so I think this is going to be where hopefully we'll be able to really push the limits of this system as we go forward, increasing rate without sacrificing an increase in overpotential. And so based on all these results, we've really been thinking a lot about this concept of mediators. And the basic question was simply, if they can function co-catalytically, why couldn't they also function electrocatalytically? And a good case study reaction for this is another one of our favorite reactions, which is the oxygen reduction reaction. So at the industrial scale, at the bench scale, oxygen reduction is great, particularly when we think about the use of hydrogen peroxide, which is an intermediate from the reduction of dioxygen to water, right, which is the 4-electron, 4-proton product, 2 equivalents of water. So at the industrial scale, we use hydrogen peroxide for detergents and wastewater treatment. And then on the bench scale, we're doing things like CH functionalization. People interested in bioinorganic active sites are interested in how oxygen reduction is occurring and how the body navigates using dioxygen for transport or the production of reduced oxygen species and superoxide dismutases, right? All of this is bound up in oxygen chemistry. The issue with the generation of things like hydrogen peroxide, of course, is that the way we make it is not very environmentally friendly. We're relying on the anthraquinone process, which has been relatively unchanged over the past 100 years, and that's using hydrogen, which is not derived from green sources, in a biphasic process with heterogeneous palladium material in order to create something on large scale that, if it's too concentrated, is a very competent rocket fuel. And so it might be nice if you could do this electrochemically under mild conditions to make hydrogen peroxide when you need it, because then you can think about using solar energy in line for wastewater treatment, right? Not all applications require concentrated forms of peroxide to be useful. And of course, as I already introduced, this was part of that electron transport chain, right? This is how nature's recovering energy from energy-rich molecules, doing the oxygen reduction reaction on one half, and then electrochemically decomposing those energy-rich molecules as part of the electron transport chain during cellular respiration. This is what we want to do for alternative energy applications. In a fuel cell, we are electrochemically decomposing an energy-rich fuel, like dihydrogen, using the oxygen reduction reaction to create that balance, that coupling of electron flow, and generate the proton flow necessary in order to actually get power, okay? So we're thinking about redox mediators for oxygen reduction. Something that is always true as a chemist is that no matter how clever you think you are, if you go looking for these things, what's probably already happened is that nature has beat you to the punch. Nature's already figured this out. It had a million years advantage on me, so I'm not trying to hate on myself too much, but it's hard to beat this, right? And so one of the prime examples here is flavinium. So flavinium does this exquisite thing where it gets reduced by NADH, reacts with O2, makes a hydroperoxide species, and then it does substrate activation, right? And people have figured this out before me. You can take flavinium, you can actually get it in kilogram quantities, and use this as a photocatalyst to do these kinds of things under aerobic conditions. It's a really fascinating molecule, but it's kind of good to think about this, right? Reducing nitrogen heterocycles. This may be a good way to figure out what we need in terms of activity. Now, there's an unfortunate second truth when you're operating as somebody in electrochemistry and homogeneous catalysis. It's that nature has necessarily often thought of what you wanted to do first, but the other person who has beat you to the punch is generally Jean-Michel Savient. And Jean-Michel Savient, of course, has already looked at oxygen reduction with organic molecules. Here's a paper from 1985 where he used methyl viologen as an electrocatalyst. And this system he characterized rather completely and saw that when you generate this radical cation, you get outer sphere reduction to superoxide. Superoxide is protonated and then reduced again by a second equivalent of that methyl viologen radical cation to get a hydroperoxide species and kind of complete the catalytic cycle. But at no point did any of this behavior in DMSO with chloroacetic acid seem to imply that there was a type of inner sphere reaction. And so there's kind of a lull in this chemistry until 2020 when Francois Gabay at Texas A&M reported the system where there was an inner sphere reaction occurring with dioxygen that allowed for recovery of the dicarbinium precatalyst. So he's got this dicarbenium species, and in the inner sphere, when it's reduced, it can capture O2 as a peroxide, and then using methane sulfonic acid, you can actually protonate this out and recover hydrogen peroxide. And so there's a lot that's very cool about this system, and you're thinking about the positioning and these kind of cooperative interactions between the carbenium centers. But something to note here from Francois' data is, of course, that these 2 1-electron reductions, that's the neutral diradical species, he was seeing increases in current at the monocationic carbon radical, right? So maybe it's possible to access this kind of reactivity at more positive potentials. And so one of my many limitations is that often it's difficult for us to do sophisticated things synthetically. And I was fortunate that my office suite mate, Mike Holinsky, is an expert on organocatalysis. And not just any organocatalysis, but organocatalysis for group transfer reactions where you begin from hydrogen peroxide as a substrate. So Mike has spent a career making molecules that are stable and reversibly interact with hydrogen peroxide. If I'm going to make a catalyst for O2 reduction, those are the qualities I need in a molecule. And what's fantastic about this is that because these are all organic molecules, this is a diamagnetic catalytic cycle. Mike can watch this hydroperoxide peroxyaminal species form via NMR, watch it decompose through water extrusion to the oxyzirridinium, and then see this do CH activation to generate hydroxylated product. So it's a fantastic molecule. And an aminium motif like this does bear a lot of similarity to that flavinium species, right? And the reason I was convinced that this would work, because I had to go on bended knee to Mike to convince him to give me some of this fantastic catalyst, was that it also works for amination. So it does nitrogen group transfer if you have a suitable source of nitrogen atom via the analogous nitrogen species to that oxyzirridinium, okay? So something we often do for these types of electrochemical reactions, particularly the oxygen reduction, is supplement what we do in terms of electrochemistry with stop flow experiments. So in a stop flow experiment, you've got these mechanically actuated syringes. What they do is inject things in very small volumes on very precise times, and you can watch reactions occur as a function of time that might be too fast to monitor otherwise. And in this case, rather than using the electrode, we use a solubilized electron source, in this case decamethylferrocene. And so the rate of decamethylferrocene appearance is related to the catalytic rate of the process, okay? And what's nice about this as a reagent is it absorbs at much longer wavelengths. This is far afield from where we see any absorption from our compounds, meaning that you can see very nice reaction progress kinetics by monitoring this as a function of time. So if you know how many of these metallocenes are being consumed as a part of the catalytic reaction by doing product analysis, you can start to extract the same kind of information we were getting from CV in the electrocatalytic systems by instead doing this electrochemical version of the reaction. And so when we looked at this in stopped flow with decamethylferrocene as a reductant, what we saw is a rate law and behavior that suggested we were largely behaving under outer sphere conditions like Jean-Michel had observed. We're generating a neutral radical species, which is generating superoxide. This is disproportionating rapidly in the presence of trifluoroacetic acid, allowing us to see quantitative production of hydrogen peroxide by spectrochemical methods. But what was really cool for us here is that we were at extraordinarily low catalyst loadings. We're seeing turnover frequencies approaching about 7,000 per second for this process. I mean, the time scale here is out to 100 seconds. This is very fast, this reaction to generate hydrogen peroxide. Now, a couple features about this we're able to get through these types of mechanistic studies is one of the things you can do for stoichiometric reactions electrochemically is vary either the scan rate or the concentration, and how your peak voltage shifts is actually indicative of the type of mechanism at play. So when you looked at this redox process by CV, it was irreversible at a scan rate of about 100 millivolts per second. So if you vary the scan rate and then the change in voltage according to scan rate, what you find is it's not a simple EC mechanism. What's actually happening is these neutral radical species are dimerizing. And we think it's because of the magic of this CF3 group. It's so electronegative that when you break that iminium bond through reduction, significant radical character is going to this carbon atom adjacent to the nitrogen. And that this allows for the possibility of a dimerization reaction, but also it turns out inner sphere reactions with superoxide when it's generated. So if you repeat that same experiment under O2, where you've got no acid present, the way that peak voltage changes with scan rate is actually different. Instead, what it implies is we've got this outer sphere process to generate superoxide, but because we're in a reaction diffusion layer near the electrode where there's a lot of this neutral radical, we're capturing it as a peroxide species. And once you have that peroxide species, all of a sudden, we're getting into a cycle that overlaps very neatly with the cycle that Mike had already discovered when he was adding hydrogen peroxide to this iminium system. Because, remember, that's one of his key intermediates. This is the other one, the oxyzirridinium. This is the thermal step that he had already reported. And it turns out that the reduction of this by a proton-coupled electron transfer is extremely facile under these conditions. And you see absolute product selectivity for water rather than hydrogen peroxide, and a catalytic rate expression that starts looking like a homogeneous transition metal complex. And so, you know, it's very rare. In fact, I can think of no other time in which I've been like, oh, I understand that these aspects are key for the thermocatalytic cycle. I think it's going to be straightforward to electrify these and get the same reactivity, okay? And indeed, you know, everything we've observed here implies that we're invoking these intermediates that Mike uses as part of these CH oxidation cycles. And so, you know, nothing breeds overconfidence like an initial success, but based on this result and some other work we were doing in lab and looking at the prior examples made us think that it should be possible to find other compounds and then also use similar approaches to optimizing them and understanding them. And so what we need, of course, is an organic molecule that's hard to oxidize. And in the course of making bipyridine and phenanthrene derivatives, we had come across this unique barrier, which is that it's very difficult to make a bis-N-oxo species out of phenanthrene. And it's because it's locked in the backbone. Those N-oxo species actually have to be stacked on one another in a helical position. And it wasn't until somebody decided to bubble fluorine gas in wet acetonitrile that it was possible to make an oxidant potent enough to force this helicalization of the molecule and get the bis-N-oxo compound. And it turns out what's true for this is also true if you try to quaternize the phenanthrene. If you use methyl iodide, those methyl groups fight with one another, and you only ever see one alkylation to form a monocation. But if you use a dibromo or a dibromopropyl or dibromoethyl species, you can get cyclization by having carbon spacers in the molecule. And this is actually the basis for doing functionalization reactions at these positions next to nitrogen. And so what was appealing to us about using this system is it's got some features in common with, you know, the acridine systems, the methylviologen systems that we had seen previously, but also some interesting comparisons to Francois' system with this dicarbinium, because these two charges are going to be electronically coupled across this phenanthrene portion of the molecule. And so this is a very crystalline material, it's very easy to work with, and it's got these two redox features which are coupled here at potentials more positive than O2 to superoxide. And so what I mean by coupled here is we've got two charges, but it takes two different voltages to reduce them. When I put one electron in here, it's kind of shared by delocalization between the two halves of the molecules. And to break that energy of delocalization, I need to go to slightly more negative potentials to see another one electron reduction of this species. So when we looked at this by CV electrocatalytically, we were pleased to see high current densities and good selectivity for hydrogen peroxide, but it was almost impossible to extract anything that looked like a reasonable rate law because we were seeing all sorts of half-order dependence on the catalyst and mixed order kinetics for O2. The other feature we saw is that with trifluoroacetic acid as a proton donor, when we decreased concentration, we were seeing an increase in turnover frequencies. And so something that's common to transition metal ORR is that dimers can form. But this was unexpected for us, of course, because the limited number of ORR catalysts that are based on organic molecules, that's not a mechanism that had been seen previously. So in order to really figure this out, we had to turn again to those stop flow techniques I introduced a moment ago. And with this trifluoroacetic acid, it's actually an order of magnitude faster for hydrogen peroxide than that original aminium catalyst, about 17,000 times per second. But something very interesting happens to the rate expression. With our fastest conditions, trifluoroacetic acid, first order in catalyst, first order in acid, first order in O2, the O2 dependence for the observed rate drops out as we go to the slightly weaker trichloroacetic acid. And all of a sudden with dichloro and monochloroacetic acid, what we see is a half-order dependence on the catalyst and a first-order dependence on acid. And so were this to be a transition metal complex, your basic assumption, of course, would be that we've got these dimerization reactions occurring. So we sought to supplement these mechanistic data and some NMR experiments with some computational studies. And what we found is, what we believe is most likely to be happening is we get this initial outer sphere reduction to make superoxide, and we're getting a radical ion pair between superoxide and the dication species. So the increased positive charge is allowing for an electrostatic association between these two species. Now there's a deformation at this level of theory at this position para to the nitrogen group, but the distance involved here is too long for a formal bonding interaction. Instead, what we think you should, the way we believe that you should really consider this is kind of the approach of a lone pair from superoxide, which is de-aromatizing, similar to what happens when you convert with a hydride between NAD plus and NADH. It's coming in here to form an interaction and de-aromatize the system, and you're seeing increased double bond character here on the outer edge, as well as more lone pair character here at the nitrogen, which was originally carrying the positive charge. So once you get to this point and dimerization becomes the most favorable thing to do, rather than reduction or protonation, this dimer species is what's controlling all of the activity we see because it's relatively stable on the potential energy surface. And so each phenanthrylene monocation is supplying one electron, and you get this bridging peroxo species where you've de-aromatized this pyridine ring on two separate equivalents. There's some stacking between them, and you see increased double bond character here and pyramidalization rather than a planarization here at this nitrogen atom. So why then this acid dependence? Why are we seeing these reactions scale this way? Well, what we think is happening after you generate this superoxide radical ion pair and get to the dimerization is we've got this acid-controlled equilibrium related to forming a hydroperoxo species and closing the catalytic cycle. What's interesting here, though, is that across an experimental 8 orders of magnitude in terms of pKa between trifluoroacetic acid and monochloroacetic acid is that the barrier for breaking up that dimer is relatively invariant. It's only when formal protonation occurs that you begin to see a differentiation and everything is more favorable or has a lower barrier when it's those stronger acids. And so the reason this work is so hard is that we're relatively early on the proton transfer coordinate for this reaction. It's a hydrogen bond interaction forcing its way in, which does enough to structurally distort this peroxo species that the energy for re-atomization provides a driving force for it to pop off. And so it doesn't really matter the pKa here, it's the hydrogen bonding interaction breaking up this dimer. And what's exciting about this is it suggests several things for continuing to optimize the system. One obvious one is that, well, this phenyl group is certainly under our synthetic control. And if we're using that to either manipulate the strength of this interaction or the localization of the radical character on the species, we can start tuning this in a way similar to what the structural activity approaches we've been using for transition metal complexes. And I'll close here just by saying that we're trying to look at this as if we would for optimizing an electrocatalytic cycle. So a divalent ion going to monovalent, reacting with O2, these kinds of interactions, this has been studied with copper ORR catalysts forever. They love making dimers. Because they're difficult to oxidize, it never goes to a state that's higher valent in terms of oxidation state than copper-2. And that's very similar to what we think, at least the way we're currently thinking about the mechanism here. The difference being is that rather than the thermodynamics of switching between different oxidation states or d orbital occupancies, we're relying on atomization, de-atomization interactions to kind of provide components that aid in these transformations. And so the question is, you know, where does the radical character matter? It's got to be harder to de-aromatize on internal positions. How is that going to affect reactivity? And where does the position on this pyridine ring matter for those types of interactions? Because you'll remember, the iminium radical was located at this position rather than the para position. So with that, I'll thank the agencies for funding, my very talented coworkers who I'm fortunate to work with, you for your very kind attention and the invitation, and I'll be happy to answer any questions you might have.
Thank you, Charlie. We have some time for questions. I don't have to do so. You have to speak loud. Somebody?
Goes first, then many thanks, Charlie. That was a great talk. I learned a lot. I have no idea. Juan tells me from time to time. So one question, when you were talking about the CO2 reduction, why is the selectivity so high, no matter which is the mediator or no mediator? You don't see any other CO2 reduction product?
So no other CO2 reduction products with that mediator. Kind of losing my, there it is. Right, so no, this appears to at least work well in this cycle, but this is, you know, what you don't convey in the overview, of course, is that in acetonitrile, it's actually very easy to reduce the sulfone. And you start seeing the sulfone be reduced rather than the CO2 thing. Now, I think it's possible to use this strategy for more reduced CO2 products, but I think the trick there is that what you want to use the mediator to do is generate what's effectively a very weak heteroatom H bond. And so this is a strategy that Jonas Peters uses for nitrogen functionalization. If I generate an element hydrogen bond that's 30 kcals per mole in energy electrochemically, that should be enough to think about adding an H atom to this species and making a metal formyl. And if I've made a metal formyl species, I can start thinking about formaldehyde, methanol, or methane as a reduction product. So I think we could. We're trying that. The challenge is, of course, when you make very weak element hydrogen bonds, they tend to be weaker bonds than the bond in dihydrogen, which means that dihydrogen starts becoming a really significant competing product. So that's kind of what we're trying to do to see more reduced products, because, as you say, that would be a very interesting strategy.
If I may, for the other story, well, the oxygen reduction chemistry.
Mm-hmm.
So if you do the reaction, you reduce the compound, the last naphthalene,
Mm-hmm.
that will show in the absence of the proton source.
Mm-hmm.
Can you get that dimer, like isolate that dimer?
Yeah, oh yeah. So, right. So what I've been doing currently here in Germany is you get this very nice radical, very nice organic radical. Where did I lose it? Okay, so we can see this by EPR. If you set this up without a proton donor present, you can see a real loss of symmetry here to the dimer species. And so by NMR, you get this very nice species. The problem is that it decomposes by mass spec. We haven't gotten a crystal structure yet, but it's clearly forming and it's relatively stable. It's only acid that actually liberates that. So it sits there a while at least before it decomposes. But In this case, it never dimerizes with a second equivalent. This is too sterically hindered. But this is very nice by NMR. You can do it stepwise. Reduce, form the O2 adduct. Then when you add the acid, it reverts completely to the starting species here. So.
That's so nice. And the thing, I guess, because I was thinking about that kind of stable radical, you could use it to other. You have been doing O2 because then it related to the reduction chemistry.
Yeah.
You could drop all the things, right?
Yes. Yeah. So we're, yeah. We're very interested in trying that now. We're working on that. There are some challenges, because you'd really like to be able to electrochemically generate something that was a good hydride source. But with organic molecules, that tends to be slow. But that would be a great entry point to doing other types of reactions. So, absolutely.
So staying in this topic, I was completely unaware. It was really nice talk.
Oh, thank you.
My question is with your knowledge of coordination chemistry and trying to expand more of this reactivity, do you think you could use them as a mediator to activate your oxygen and form oxo species to transfer oxygen atom to
Yeah, so just doing the flavinium version, synthetically, right?
I mean, it depends on the potential. If that you need to find that metal so you will use the organic material to form your oxo metal species, and then that can act as an oxygen atom transfer, right?
Yeah. So, yes, the problem is matching the rates. But yes, I think you could do that to have the transfer.
I don't know how stable is that. Once you have the peroxo activated in the species number 3.
Yeah.
So I don't know how easy it would be that you put a metal and the metal just take that 2 oxygens and transfer all
Yeah.
1 oxygen, right?
Yeah. So I think that what you're describing is what we're going to need to do to make this electrocatalytic for CH functionalization, because this species is active for CH functionalization, but it's slow by itself. And what we do faster than that reacts with something is keep on reducing it. But what you're saying is if we remove the proton source, and then, and that's like using like a Lewis, or even just like a strong Lewis acid, right? Even something redox inert, and then you could. That is a great idea. We haven't tried that, but we should. I think that could work.
The other?
Amazing talk. Not long ago, we had Professor Robert here,
Mhm.
and he presented the cobalt halocyanins, and he showed that go beyond CO
Mm-hmm.
when they were the planarity was distorted.
Mm-hmm.
But the inner coordination of mediators in chromium will not be possible because the CO quick dissociation is a blessing and a curse. So
That's right.
Can you, or do you envision that this can happen, that you can supercharge your catalyst to go beyond CO?
Oh, just for the chromium species? Well, I emphasized that CO binding wasn't happening in the regular CO2 reduction cycle, but as far as I understand it for the phthalocyanine, based on the amount of reduction of that phthalocyanine, that's impacting very heavily the coordination of that CO molecule as well and relates to that activation. And so if it were to work with this catalyst, we would have to go to much more negative potentials where it hasn't been stable yet. But if you could go to even adding another electron and stabilizing CO without it decomposing, you'd have a shot. That's the real magic of the phthalocyanine, is it's such a stable compound, you can form these reduced carbonyl species and then go down to the 4-mel, right? And so, I think we'll have to make some structural modifications before chromium can do it, but it shouldn't just be magic for cobalt, because what you're playing with is how strong is that CO interaction and how easy is it to weaken it enough that 4-mel species become accessible. Because organo 4-mel species, you can, transition metal 4-mel species, it's very easy to do additional chemistry. So it should be accessible, but the phthalocyanine does raise some questions about how we'll change other compounds to match what that can do so well.
Curiosity, Charlie.
Yep.
the activity of the free metal catalyst that you use is comparable to the common metal catalyst that is normally used in this oxygen reduction?
For the oxygen reduction reaction, so the fastest catalysts which are known for oxygen reduction are iron porphyrins, and they can turn over on the order of about 1 million times per second. The difference is that the overpotentials being used there tend to be a little bit more negative. So there's a greater driving force. But obviously, 17,000 per second is nice, but what we want to do is that extra order of magnitude or two, and then think about this. Because something I didn't mention, but which is relevant to these kinds of studies, is that there's a lot of work going on to make carbon-based catalysts for oxygen reduction, heterogeneous materials, where they take reduced graphene oxides, and in the presence of nitrogen, they get these materials that do ORR. And I'm very curious to see if these are kind of models for what they kind of get out of those heterogeneous species. And if so, maybe we can put something on the surface more deliberately and make better carbon materials for that ORR reaction.
And what about the stability? One can imagine that the stability is much better, no? With this.
Yeah, so as far as we can tell, the NMR experiments are great because you can see this stoichiometric conversion back and forth. You add ferrocene, you see the loss of your diamagnetic signals because you're making a radical. You expose to O2, it snaps into diamagnetic structure again where you've clearly lost this symmetry plane in between the two halves. And then you add the acid, it reverts all the way back to what the starting material looks like. So I think this is reasonably stable. We haven't gone till loss of activity yet. So that would be a good experiment to check. But I mean, if these heterogeneous carbon materials are working, I mean, there's a reasonable chance this could as well.
Thank you very much.
Yep.
So let's thank again.
Thank you.